Okay, so this will be the 8th lecture on Z-transforms, all part of Chapter 5. It'll be the last lecture we need for Chapter 5. We're going to look at two examples in this particular lecture to wrap things up. One, we will do another example on frequency response. We're going to go ahead and plot the magnitude response and phase response for a complex system rather than a real system. And then in the final example, we're going to look at a non-standard implementation of a discrete time system and use what we know about Z-transforms in order to answer some basic questions about that system. So let's go ahead and think about this first example that has to do with frequency response. So frequency response. And I would like to do this one, as I said, for a system that is complex. So let's take a look at this particular example. I'm going to have a system, h of z, so I'm going to define it using its transfer function. H of z is equal to z, and then I'm going to have a plus j in the numerator, and I will have a z minus j by 2 in the denominator. So if you think about this transfer function, it's a rational function, first order polynomial in the numerator, first order polynomial in the denominator, so it's a first order system. And because the coefficients in the expanded form are complex, we know the system is not real. It is a complex system. I would like to go ahead and be able to plot using that pole zero information, the magnitude response, magnitude h of e j omega. And I would like to be able to plot as a second thing, this angle or phase response, angle of h, e, j, omega. So getting magnitude and phase responses for this system using pole zero information. And then the last thing that I'd like to use that magnitude and phase information for is to determine the output yn in response, right? The output in response to an input x of n being equal to 1 plus cosine of pi by 2 times n. So I'm going to have a input x of n that is comprised of a DC component and then a sinusoid as well. And we'd like to figure out what this system does for an output on that particular input. So let's go ahead and start. We know that when we want to plot magnitude and phase information that we need to identify where the poles and zeros are, and it's really the relationship that pole and zero to different frequencies that will help us get those sketches of both magnitude and phase. So I'm going to go ahead and plot out my complex z-plane, right? And we know the horizontal axis is the real part of z, and the imaginary axis, the vertical axis, is the imaginary part of z. I'm going to go ahead and try to draw the unit circle here for reference, just so that we know where everything is in relation to that unit circle. We know the unit circle is where sinusoids live. It's our boundary for stability for discrete time systems as well. So taking a look at the numerator of h of z, I see a z plus j, set that equal to 0. I get z plus j equaling 0. Solve for z, and I see that I get a 0 at z equaling minus j. So that's down here, right, at the bottom of that unit circle. I've got a 0 at a point z equaling minus j. So I'll go ahead and label that. There is the system 0 at z equaling minus j. In a similar way, I can look at the denominator of h of z, and I can set it equal to 0. So I have z minus j by 2 equaling 0. Solve that for z. That gives me z equaling j by 2. So I have a pole at the location j by 2. So that's halfway up the imaginary axis at a value of 1/2, right? And we might just label that as well, that we have a pole then, right, at z equaling j by 2. One of the ways that we can easily tell that this system is complex just based on the pole zero plot is that we have complex roots, right? Both a complex zero and a complex pole, but they are not paired with a conjugate partner or conjugate friend. So for real systems, any kind of complex root must come in conjugate pairs. We don't have the conjugate pairing here, so we know for a fact that this must be a complex system. What is a complex system? A complex system is one that even if you give it a real input, it's not guaranteed to give you a real output. It might end up turning that real input into a complex output. So we're going to use this pole zero information to try to get a plot of both the magnitude response and the phase response. I'm going to go ahead and start off on the right here to give myself a graph for what that magnitude response might look like. So I'm going to go ahead and put my graph in here. We're going to label that graph as the magnitude of H, E, J, cap omega. So it's the magnitude response. If you remember from the previous lecture, we said that frequency response is comprised of the magnitude response and the phase response taken together. Frequency response is a 2 pi periodic function of the frequency variable cap omega. Because it is 2 pi periodic, we really only need to figure these guys out over the interval, or a interval that is 2 pi wide, and it's most common to pick the interval minus pi to pi, and I'm going to go ahead and do that. So I'm going to look at this magnitude response over the range minus pi to pi. A couple of things that we might notice in here is that I've got a 0 on the unit circle, and that occurs at a frequency of cap omega equaling minus pi by 2. So if I come over here to minus pi by 2, I know for a fact my magnitude response is going to be 0 there, just because of the presence of that 0 at that particular frequency. I had to go from the DC point, right, in a clockwise direction, right? So those are going to give me negative angles, a clockwise direction of 90 degrees, or pi by 2 radians, so minus pi by 2 in there. That gets me down to that 0, and that's where this overall transfer function has to be 0. That's what the definition of a 0 is. So looking at magnitude H of E minus J pi by 2. So looking at that frequency minus pi by 2, going down minus 90 degrees, if you will, we know is equal to 0 definitionally. That one's an easy one to do. I'm going to do the opposite side of this as well. I would like to look at the magnitude response of H, E, J pi by 2. And here's where I'm going to use what we learned last time about finding magnitude response as the size of the overall coefficient out front, and then distances from poles and zeros to the frequency point of interest, taken in ratio, taking those distances from the 0 to the frequency of interest divided by the distance from the pole to the frequency of interest. So going back and looking back at my original transfer function, I see that there really was not a very interesting outside coefficient. You could have thought of that as 1 times all of that. My B0 here is 1, and so it's not going to contribute anything terribly interesting to the overall magnitude response here. So I might notice just from this guy really quickly, right, that my V0, my overall gain factor in this case, is equal to 1 in this particular case. So when I think of the magnitude response then at e to the j pi by 2, something like that, I need the magnitude of V0, that's going to be 1. And then I need what? To multiply by the distance from the 0 to the frequency of interest. I'm going to go ahead and draw that in red. So the place that we're at is at a frequency pi by 2, right? That's up at the top of the unit circle. I'm going to go ahead and draw a vector from the 0 to that frequency of interest, right? And we know that that has a whole overall length of 2 units. And so the numerator here is going to be 2, something along those lines. When I think about what I need to divide by, I need to divide by the distances from all the poles to the frequency of interest. There is only one pole here. I'm going to do this in blue. So if I take that pole and I measure up to the point of interest, again, that's the top of the unit circle. That's where frequency cap omega equaling pi by 2 is. That distance only had to go 1/2. So I'm going to have a 1/2 in the denominator. Now, if I carry out that calculation, I get a total value, or a total gain, of 4 at that frequency pi by 2. So coming over to my graph, I'm going to come over at pi by 2. That's halfway between DC and the highest frequency, pi. And I know at that particular location, 1, 2, 3, 4, I have a total gain, right? I found that in there. I have a total gain of 4, something along those lines. So this definitely begins to scream that this system is not real. What do we know about real systems? Real systems have even magnitude responses. We see here immediately, just with the 2 points calculated, that there's no way that this system can be even in its magnitude response, because the gain at minus pi by 2 is 0, and the gain at pi by 2 is 4. One is not equal to the other. There's no way of getting that reflection about the omega equaling 0 point on this graph. Well, it's not a very high system, so we probably don't need to do too many more calculations. I'm going to probably do two, and one I'll get for free with symmetry, but let's go ahead and take a look at the DC response of this system. If I take a look at the DC response of the system, we're looking for magnitude H of EJ0, if you will, the DC response. We still have that size of the overall coefficient out front, B0, that's going to be 1. I need to take the distance, right, from the 0 to that DC point. So I'm going to go ahead and add in where the DC point is. We know that's at Z equaling 1. I'm going to be measuring from my 0 to that point. So we're going to measure that vector going from the 0 to the frequency of interest here at DC. We know that the unit circle is radius 1. So I have a right triangle that can be thought of here, and I'm looking for the hypotenuse of that right triangle where the two sides, right, are each 1 unit in length. So that hypotenuse has a square root of 2 length. So I should get in here a square root of 2 as being the distance, right, from that 0 to the frequency of interest in this particular case where DC is at. So I'm going to go ahead and leave that in there as well. If I want to think about the pole's contribution, so the pole is the thing in the denominator, I still need to draw the vector from that pole to the frequency of interest, and I need to find its distance. So I'm going to go from the pole, right, to the frequency of interest. That's also viewable as a right triangle. It's just one base is 1 unit in width or length, and the other base is 1/2 unit in length. And so using the law of right triangles, so I can find its hypotenuse, that length of the green or the blue line sitting there, I'm going to take 1 squared plus a 1/2 squared, that's going to be 5/4, and take the square root of that, that's root 5 by 2. So I should have in the denominator root 5 by 2. Something along those lines. So if I go ahead and just play with that just a tiny bit, I should be able to get in here a 2 root 2 divided by root 5 as being my overall gain for my DC point. That's not a terribly nice number, so I'm going to go ahead and pull out my calculator in this particular case. I'm going to take 2, and I'm going to go ahead and take its square root, and then I'll take it 2 times that, and then I'm going to take the square root of 5 and divide by that. And what I get in this particular case is a 1.2649. So go ahead and calculate that out. I get 1.2649. Just want to get a nice decimal number so that I can put it reasonably accurate on my graph. So going back to my magnitude plot, I need to go basically 1 1/4 up at a DC frequency, so cap omega equaling 0. If we remember here, we are looking at the horizontal axis as being that frequency, cap omega. So I'm going to come up here and I'm going to go up about, what, 1 1/4, something along those lines. Well, there's another point here that we can get for free basically on that, and that's because of a different kind of symmetry that just happens a little bit luckily, as the case may be, for this particular system to have, so that I can get that high frequency gain as well. I'm going to be looking at the magnitude of HEJ pi. So if I did a very quick just sketch of what that would look like, there's the high frequency point, that is cap omega, right, equaling pi, something along those lines, which also is equal to minus pi. We can use either one of those. We can use cap omega equaling pi or cap minus pi being my frequency cap omega. Either one of those will get us to that leftmost point on the unit circle. The gain here is going to be involving a distance, right, going from the 0 to the frequency of interest. Well, that's just a reflection of what we just computed. We know that's still going to have a length root 2, and in the same sort of way, going from the pole to that frequency of interest, we see that that guy also has the same length. That was going to be that root 5 by 2. So just by a symmetry argument here, we can see that these guys have exactly the same values. That's also going to be a 1.2649. So if I look at where that guy is, right, that one that we had just computed, we know that that also happens to be for my high frequency point, which is at both pi and minus pi. Now I probably have enough values in here that I should be able to go ahead and get a reasonable plot in this particular case. So I might do something like this, that I get a overall response that looks something like that. We'll verify this with MATLAB, get something a little bit more accurate later. But what do we see in this case? We see a system that strongly, with a gain of 4, right, strongly responds to frequencies in the vicinity of kappa omega equaling pi by 2. But it does it in kind of a weird way, right? It strongly responds to pi by 2, but it absolutely hates frequencies of minus pi by 2. So here is one that is not only frequency selective, but it's one that favors, in this particular case, the positive frequencies. This is a little bit like a kind of weird bandpass filter, right? It's allowing a band of frequencies near pi by 2 to go through, and it's trying to get rid of, at least as good as a first order system can do, everything else. So we have a sort of strange system, right, that is going to allow frequencies on the positive side through much better than negative frequencies. So what can we do? So the next thing that we're going to look for is the phase response. Our last lecture, we learned that the phase response, or the angle of h, e, j, omega, can be gotten by the angle of our overall DC constant, right, or our overall constant B0. We're going to add to that a sum of angles, right, that involve going from the 0 to the frequency of interest. And then we're going to subtract out, because they were in the denominator, the phase or angle contributions of the poles going to the frequency of interest. So in order for us to carry this out, I'm going to go ahead and repeat or redraw our pole zero plot, and then I'll get the axis set up for the actual phase response itself. So go ahead and draw the complex z-plane. I'm going to go ahead and see if I can get that unit circle drawn in for reference, just like I always try to do. So I've got something that looks like that unit circle. We know that we had a 0 at minus j, so I'm going to go ahead and put that 0 in. We know that we had a pole at plus j by 2, so I'm going to go ahead and put that pole in as well. That's my pole zero plot for this first order system, and I'm trying to get out of this my phase response. So I'm going to go ahead and set up my axis for that phase response. We know phase can be plus or minus, so I'm going to let that phase values go negative as well as positive. And so we're looking here for the angle of h, e, j, omega. Phase response, just like magnitude response, is part of the frequency response, which we know to be a 2 pi periodic function. So I just need to find phase over a 2 pi interval. I'm going to go ahead and pick, just like I did with the magnitude response, something that covers the principal range. So I'm going to go minus pi to pi and see if I can find my phase contribution or my phase components over that interval. I need to go ahead and select a few test points to try to find the phase. I'm going to pick one that's easy in this particular case to compute. So I'm going to go ahead and look at a phase component associated with that frequency, kappa omega equaling pi by 2. So I'm going to go ahead and identify that on my unit circle. That's at the top of the unit circle. So this point here has my omega equaling pi by 2. That's the particular frequency that I'm going to be looking at for in this particular case or this calculation. So I'm looking for angle of h, e, j, pi by 2. The B0 for our particular transfer function was just 1. Its phase is 0. So I'm going to have 0 from B0. I'm going to add to that the phase in going from the 0 to the point of interest, right? So I'm going to go ahead and draw that with my red line. I'm going to go from the 0 to the point of interest, that point straight up. And so when I measure its angle relative to the positive real axis, I see that that is a 90-degree phase. So I'm going to have a plus 90 degrees in there. I'm going to switch colors over to blue to take care of the phase from the pole. Now the pole to the same frequency of interest to that kappa omega equaling pi over 2 still points straight up, right? And measuring that guy's angle relative to the positive real axis, right, is also 90 degrees. So because it's a pole though, I get a minus, right? And I'm going to have in here 90 degrees, something along those lines. If I carry out that calculation, I get everything coming up to be in a total sum of 0. So I know at that frequency pi by 2, I end up getting 0 phase adjustment. If I put a everlasting sinusoid of frequency pi by 2 in there, the magnitude response told me it would get a gain of 4, and this phase response tells me the phase would be unchanged. So there would be no phase offset or phase alteration with that frequency pi by 2. So that's one of our calculations, not too bad. If I look at the other side of the circle, if I come back down to the frequency at minus pi by 2, so I'm going to color that in dark again. If I look at that guy, that's a little more problematic to compute, right? Because trying to measure the angle from the 0 to that point, because they're the same point, we're never going to be able to get a phase measurement at the exact frequency minus pi by 2. We'll use the same technique that we did in continuous time. I'm going to look just a little before and a little beyond that frequency minus pi by 2 to see if I can get these phase calculations. So let's go ahead and start out with the angle response of h e to the minus j pi by 2, but just go a little short of that. So I'm going to call it pi by 2 minus. That means just a little short of pi by 2, and it's all minus. That means it's a little closer to DC than the full angle minus pi by 2. I'm going to go ahead and draw a little bit of a blown up or a zoomed in portion of our picture here. So we have our 0 sitting there on the point z equaling minus j, right? And I'm going to be picking a frequency that's just a little short of that point. So I'm picking a frequency something like that, just a little bit off, but towards the DC side. If I go ahead and I think about what the phase is on this, the DC term, B0 still has 0 phase, so no problem with that. The phase contribution from the 0 though now, right? The 0 pointing just a little bit short of that, it's just pointing straight off to the right. That is going to be a 0 degree component. So we know that we are going to get no particular phase component from that 0 in looking just a little bit short of it, right? It's going to be pointing right off immediately to the right. I'm going to go back to my other pole 0, the one that shows the full thing, to see what the phase component would be from my pole. My pole is going to be pointing straight down there. It doesn't matter that I'm just a little bit too short or a little bit beyond. It's all going to be pointing straight down. The angle there is minus 90 degrees, minus 90, right? Minus 90 degrees, taken relative to the positive real axis. Because it's a pole, we subtract that phase. So I'm going to get minus of a minus 90 degrees on there. And if I carry that all out, I end up getting 90 degrees. So my phase response is 90 degrees when I'm just a little bit short of, just haven't quite gotten to minus pi by 2 when traveling from DC, something along those lines. We will draw that out here on my graph. Go ahead and put a vertical line along here. I'm going to go ahead and give myself a minus 90 degree point, and I'm going to give myself a 90 degree point, something along those lines. We just said that this was 90 degrees when we were just a little short. So I'm going to go just a little bit to the right of that dotted line, and I get that point up there at 90 degrees, something along those lines. When I go to the other side, the angle response, HE minus j pi by 2, but I go just a little beyond, so pi by 2 plus, a little bit more than pi by 2, traveling a little bit beyond there when traveling from DC. I still get 0 from my B0. 1 has a gain or a phase of 0. And when I look now at my phase contribution from the 0, I'm going to go over there to that zoomed plot again. We're looking now at a point that is just a little bit beyond, right? So it's a little bit past that 0 now. And if I look at the phase contribution from that, now the phase contribution and going from that 0 to the frequency of interest, it's pointing directly to the left, right? Just directly to the left. That's a phase of 180 degrees. So I'm going to get plus 180 here, right? And then I need to figure out the phase component from my pole. Well, that hasn't changed. It's still pointing down towards that 0. We're just a little to the left or a little to the right of it, but that pole is so far away, it's still pointing down at a minus 90 degrees. So I'm still going to get a minus of a minus 90 degrees in there. If I carry this out, I'm going to get 180 degrees plus 90. That's 270. I could write it as 270, but I also know 270 is the same as minus 90 degrees. I'd like to keep things in that phase range of minus pi to pi, or minus 180 degrees to 180. You don't have to do that. It just turns out to be convenient. So knowing that just a little beyond minus pi by 2, I get minus 90 degrees. I'm going to go ahead and draw that in here as well. So if I do just a little to the left, I'm going to get that guy being at minus 90 degrees. So we're making some progress here. Probably don't need that many more points. I'm going to do maybe one more, and then we'll just see if we can sketch them in at some particular way in there. So let's go ahead and see if we can do something about a DC gain or phase. So angle of HEJ0. I'd like to find out what is the phase change at DC. Well, in this particular case, because the system is complex, we don't only have the options of 0 or 180 degrees. Remember, a real system, if you had a DC signal going in, that constant, because a real system has to keep things as real, we know DC values can either be plus or minus, and that's the only way they can stay real. Now that I have a complex system, a DC signal like 1, for example, could come out as any complex number. So it could have really any phase. So really, we've got a lot more options here. The overall transfer function B0 still has that, B0 equaling 1, which has a phase of 0, so that's not going to change. We just now need to figure out what the angle contributions of my two pieces are. So I'm going to go and do the 0 first. If I take a look at where DC is on my original pole 0 plot, DC is sitting there at the right side of the circle, right? We're going to go from my 0 to that frequency of interest, right? And what do we get there? We get an angle of 45 degrees when measured from the positive real axis. So I'm going to have a plus 45 degrees on this guy. I need to subtract from that, right, the phase contribution from my pole. I'm going to do just a little bit of erasing here so that I can make a plot in here. And what I know is I'm going to be going from my pole, right, to that frequency of interest as well. And so I need to be able to get that angle sitting in there. That angle, right, is going to be something like what? The arctangent of a half. So that is a tan of 1/2, something along those lines. So I'm going to go ahead and grab my calculator and see if I can get this guy done as well. I'm going to put in 0.5 and I'm going to look for my arctangent function. I'm going to go ahead and do that. That gave me a radian measure in there. I'm going to go ahead and compute it to degrees. So I'm going to take that radian measure and I'm going to take 180 degrees, multiply it by that, and then take a value pi and divide out that pi. So 3.14 divide on there. And what I get is 26.6 degrees roughly, 26.6. We can see that that's a negative angle the way it's drawn, so we're going to get a minus 26.6 degrees somewhere in there. So if I take 45 minus a minus 26.5, 45, 55, 65, 71.6, something like that. We should get something like a 71.6 degrees. So I'm going to go ahead and add that in there as well. If I go to my original graph, we were looking at the DC part, 71.6, right? If I think of that as a ratio of values, I could put 71.6 and look at what that ratio is. That's about 80% of the 90 degrees. So I need to go up about 80%. I'm going to call it something about like that. We need something more accurate. You can do it using like MATLAB. I'll just label it in there that that's 71.6 degrees, something along those lines. Okay, so what would I expect my phase plot to look like? We know that we had to have transitioned, right, from the 90 degrees, it was just a little short of minus pi by 2, to 71.6 at DC, all the way down to 0 at pi by 2. And then that's going to have to keep its trend down until we hit pi, which is the same value as minus pi, in which case it continues its transition to minus 90. I'm going to do it rough now at this point, and we'll see if we can do that. So I'm going to start at just a little short of minus pi by 2. And I know that I have to get through that 71.6. That has to continue on and hit that 0, right? And what it has to do is it has to probably continue that same trajectory, and whatever I just hit there, right, at pi, is where it pops out at minus pi, because this is a 2 pi periodic function. And so I'm going to pop out at that minus pi, and then that has to make its way down to minus 90, which was the other side, just going a little beyond minus pi by 2. So I get kind of a wonky phase response. You'll see it is not an odd function. Real systems would have an odd symmetry in the phase response. Complex systems do not necessarily have that. Each different frequency in that interval minus pi to pi has its own different value of phase alteration. We've done enough calculations here, we can probably get pretty close. What I would like to do is just take a quick aside. I'm going to switch applications over here and look at some graphs that I had done with MATLAB that are calculating these guys out a little bit more accurately. So let me jump over to that. And what I have now are some MATLAB calculated versions of this magnitude response and the phase response. And what we'd like to do here is just verify in this that we did indeed get some values that we had computed previously. Let's look at the magnitude response first. This goes over the interval minus pi to pi just to clean up the horizontal axis. I'm plotting it as a function of kappa omega by pi. That's a normalized digital frequency, so it's going to go -1 to 1. 1 there would mean high frequency, this digital frequency of pi, right? And so DC, what did we get for a gain of DC? It was like 1.26. Does it look like in this particular case that we get 1.26 on there? Absolutely, looks just about right. We know that at pi by 2, or in this case, if I took pi by 2 divided by pi, that normalized frequency, that's a half, we had a gain of 4. And we see that as well. We got that confirmed gain of 4. We know DC was the same value as the high frequency because of the symmetry, so that 1.26 should have also been at pi, and it should have been at minus pi. And we see that those guys are all the same in there, right? We get all of those guys on the same line as expected. Frequencies that are positive frequencies tend to get the higher gains, yeah, stuff near that 4 gain, and lower frequencies in the negative side, right, near minus pi by 2 get killed. And in fact, at minus pi by 2, we see that gain of 0, right? That's when we went through and hit that system 0. We go to the phase response, that same frequency minus pi by 2, we see that 180-degree phase transition as we pass through the 0, as we would have expected. On the DC side of that, it's at 90 degrees. Going on the other direction, we see it's at minus 90 degrees. If we go to the DC, so we had plus 90, right, on the DC side of it, and minus 90 on the high frequency side of that minus pi by 2 frequency. We had done a calculation of the phase response at that system frequency of pi by 2 where it has the strongest gain, and that was 0, and it sees MATLAB computed that guy out exactly right as well. At DC, we said it was 71.6, and it turns out that that's exactly what MATLAB gave us as well. And then we did some sketching, right, that we sketched those guys to fit in, right? And then we said it had to hit down and hit that 0, and then it had to transition out in such a way that the trajectory continues until it hits that 90. So I think we did a pretty good job for as few calculations as we did in getting both magnitude and phase response. If you're interested in the code that does this, the code in this particular case is very straightforward. I'm going to go ahead and just show this very quickly. What did I do? I went ahead and set up an anonymous function that just basically put in that transfer function as a function of the variable z. I set up a frequency variable that went minus pi to pi with a sufficient number of points to make a good set of plots. I did a subplot to do the magnitude response. I did a different subplot to do the phase response. For the magnitude one, I plotted that normalized frequency, omega by pi, by the absolute value of h, substituting z with e to the j omega. So magnitude response definition in there. All this other stuff is just to make the plots pretty. In the phase response, it's all the same thing. I used normalized frequency here, and instead of absolute value, I used angle, and it's still of h substituting z with e to the j omega. I did use a times 180 divided by pi so that I could get the angles in degree measure rather than radians. It just made more sense when we were doing hand calculations. We're more comfortable or familiar with degrees, but really any of the typical phase measurement conventions is fine. Whether you want to do degrees or radians is perfectly okay. Everything else in there is just to give me nice axis labels and the like. All right, so let's go back to the lecture and see what we can do to finish this out. Okay, to finish this example out, we just need to find the output y of n in response to the input x of n, which we said was 1 plus cosine of pi by 2n. So we need to find the output on this. Fortunately, we've done all the calculations we need to solve this problem in earlier parts of the problem. So we see that there's 2 components to the input, a DC component 1, and then there's this intermediate frequency cosine pi by 2n. If I want to know what that 1 does, I can deal with that 1, right, is just 1 to the n, so 1 equals 1 to the n. That's an everlasting exponential going into my system. I know what's going to come out is 1 to the n times h evaluated at that same value of z, h of 1. We had from before that our h of z, right, was equal to z plus j over a z minus j by 2. If I go ahead and plug in z equaling 1, I know that this 1 to the n, or this DC term, is going to come through and get modified as 1 plus j over 1 minus j by 2. If you take your calculator and do those calculations, get a regular rectangular form, you can go through that simplification step. And what you find out getting in this particular case is that you're going to get 0.4 plus 1.2j coming out. So a DC1 is going to come out as a complex number. It's a complex system, so we expect that. It's going to come out as 0.4 plus 1.2j. Different type of DC, a complex number DC. When it comes to the other term, the cosine of pi by 2n, we know that through Euler's, that's 1/2 e to the j pi by 2n plus a 1/2 e to the minus j pi by 2n. We had dealt with the frequency response, the magnitude and phase response for frequencies pi by 2 and minus pi by 2. If you recall, pi by 2 is where the system really responded well. So that particular frequency, right, had a gain, a magnitude h equaling to 4, and its phase was equal to 0. And for the minus pi by 2, this is where the system really hated it. Magnitude response was 0, and it didn't really matter what the phase was. So is that cosine pi by 2n, which is split into two parts, a positive frequency component and a negative frequency component. These are the most basic units of frequency. We know that as that goes through my system, the first one gets multiplied by a magnitude 4, no phase change. So what's going to come out of that is a 2 e to the j pi by 2n. And the second one is completely killed because of the gain equaling to 0. What this gives me in the end is my output y of n. Y of n is equal to the DC1 became 0.4 plus 1.2j, right? And then the second term, the cosine term, only half of it survives, but it comes out 4 times as strong, and we end up getting that 2e to the j pi by 2n. That's the response to that DC offset sinusoid. We finished our example of computing frequency response for a complex system. We have just one more example that I'd like to do to finish this chapter out, and that's taking a look at a non-standard structure, okay, one that is not like a direct form 1 or a transposed direct form 2, a little bit non-standard structure implementation of a discrete time system, and see if we can answer some questions with it. So let's go ahead and try this example. So this is a different example where we're going to just look at a discrete time system that doesn't have one of the recognizable realizations and see if we can understand its behavior. So this system, like all of our discrete time systems, is going to have an input x of n. I'm going to let that input go through and feed into a summing node. So I'm going to have a summing node sitting in there. That's going to feed into another summing node in here. So we're going to go ahead and let that continue on, transition on to another summing node. And out of that summing node, we are going to get our output y of n. I'm now going to go ahead and put in the remaining part of this structure. I'm going to go ahead and take the point between these two summing nodes and let it run into an overall gain block. I'm going to call that A. That gain block is then going to feed into a delay block, z to the minus 1. And then I'm going to have that come out. There will be a pickoff node there, but it's going to continue. It's going to go through another gain block, A, and through another delay block, z to the minus 1. And then I'm going to feed that second delay block's output all the way back to that first summing node. So we're going to go ahead and do something like this. And then the pickoff node that was between the two delay blocks, I'm going to go ahead and feed that forward and have that go to the second summing node. So I've got a structure here that relates output to input through some scales and delays of both output and input. What I can tell you is that this is a difficult structure to analyze in the time domain. If you're interested in this, I'd really encourage you to go ahead and pause the video. Pause the video right now and see if you can come up with something like, can you determine what is the system transfer function h of z? What is the system unit impulse response h of n? Something like that. Can you tell me about stability of this system? Stability. What conditions would be necessary for the system to be stable? What is the output y of n, right, in response to an input x of n being equal to, let's do it as something like 1 plus cosine of pi n. Some basic questions on the system. See if you can answer these from a purely time domain kind of analysis. I think you'll find it challenging. Once you've done that, I encourage you to restart up the video and we'll look at a different way of analyzing this guy. Okay, so hopefully you've done that. What we're going to try to do is see if we can find a better way to analyze the system. If you do a purely time domain analysis of this, I do think you're going to get stuck in the feedback loops and trying to figure out which path goes to where and how to incorporate those feedbacks that aren't in a standard way. Really tough to get the difference equation or any of the other kind of quantities that were asked for on the left-hand side just by doing time domain analysis. It's really, really hard. We could, in this particular case, instead employ a transform domain approach on this. Here's the key that I think that we need to do on this. This middle part of the structure is not labeled right now, and that doesn't really help us get a set of equations that we can work with. So I'm going to go ahead and label that first top node an intermediate variable. It's a variable of convenience. It's a signal of convenience that just is going to give me a way of kind of keeping some accounting. That variable v of n is going to get multiplied by a, so that's a v of n delayed by 1. That's going to come out a v of n minus 1. And that's going to go forward. From that, then, I should be able to get some difference equations. And then from those difference equations, I should be able to answer some of these questions. So what do I know? Let's write an equation for the output y of n. What is y of n? We can see it's directly v of n, right? It has two terms, plus, and we can see in there, there's an a v of n minus 1. So that's one of the equations I have. This would not be sufficient to leave it there because while I have an output y, it has this intermediate variable v and no x's. We don't want to see any v's in there. We only want to see x's and y's. Now I can write an expression for v of n. What is v of n equal to? We see that it has the input directly getting summed into it, but then it's also got in there, right? If we continued that path along, this node that was right there in the middle that we used for y, when I get down here to this next point, what is that? That was the first node, avn minus 1, multiplied by a, so that's an a squared, and it had been delayed again, so that's a vn minus 2 point in there, something along those lines. So that's also getting added in to make up what is my vn. So I'm going to get an a squared, and I'm going to have a vn minus 2. These two equations, I just wrote equations for the output of each summing node that's in the structure. These two equations should be enough that I should be able to get a regular constant coefficient linear difference equation description for the system. The problem is that the first one gives me the output, but no input. The second one gives me an input, no output. The connector between those is the v's, but neither of those two expressions can be expressed purely in terms of v. They have v's and delays, and because the delay can't be broken away from the variable of interest in the time domain, it is really, really hard to solve these guys with time domain kind of techniques. So instead, what am I going to do? I'm going to take both of those expressions and I'm going to z-transform them. I know that z-transforms are great in that they decouple that delay operator from the variable of interest. So the first one is going to be like this. I'm going to get a y of z equaling v of z, right, plus an a z to the minus 1 v of z. What I've done now is I've decoupled that delay from the variable v, and that's going to allow me to solve for that variable v. Let's do that now in this particular case. I can solve for v of z as being equal to y of z. What was the term that I factored out from v of z? It was a 1 plus az to the minus 1. I'm going to have to divide by that to solve for v. So I'm going to have a 1 plus az to the minus 1. That's an expression for v based on this first equation, right? Yn equals vn plus avn minus 1. I'm now going to take a look at the second equation. So we did the first equation. Now I want to deal with the second equation and its z-transform. And what do I get? I'm going to get v of z as being equal to x of z. And I have a plus a squared z to the minus 2 v of z. I'm going to go ahead and solve for v of z in this particular case as well. That will require me to take that v term on the right-hand side, subtract it over, pull out the v, and divide by that factor that multiplies v to just get v by itself. That's not too hard to do. So I'm going to get a v of z equals, right? I'm going to have x of z, and the factor that I would have had when I brought that other term to the other side would have been a 1 minus a squared z to the minus 2. So I get a 1 minus a squared z to the minus 2. I have two expressions for v. V is equal to v, so I can just set those two expressions equal to one another. And that's going to give me something that just has x's and y's. That's really what I was searching. Okay, so what do we get when we set v equal to v? We get this idea that y of z by 1 plus a z to the minus 1 will be equal to x of z by 1 minus a squared z to the minus 2. This is exactly the expression that we wanted. It's purely in terms of the output variable y and the input variable x. From this, we can start getting some of the things that were asked for. Notably, we wanted that transfer function h of z. During our previous lectures, we knew that a transfer function can be gotten as a ratio of output to input, y of z to x of z. If I just rearrange the expression that we just received, we can solve for this transfer function h of z, the ratio y to x, as being equal to, and I'm going to have a 1 plus az to the minus 1 in the numerator, and in the denominator, I'm going to have a 1 minus a squared z to the minus 2. If I factor that denominator, I can get a little bit of a simplification here. Actually, let me first get it in terms of positive powers of z. I can multiply top and bottom by z squared. That would give me a z times z plus a in the numerator. And I'd have a z squared minus a squared in the denominator, which I can factor as a z plus a and a z minus a. Something that we'll notice here, that there is a pole and a 0 that cancel one another. So a simplified expression for h of z would be equal to z by z minus a. We could go ahead and box that. That's our system transfer function, the z transform of the unit impulse response. And it is reflective of a first order system, but because that pole canceled with the 0, it would be just as fine if you wanted to leave this as a z squared plus a z over a z squared minus a squared. You could certainly do that as well, but I think the simplified form is probably the preferred one, at least for representing this h of z. I can inverse z transform this kind, right? So I can take the inverse z transform of that to obtain the unit impulse response. Now that cancellation of the pole and 0 both located at minus a is very helpful. I don't have to do a partial fraction expansion. I can look this up directly from my tables. This has a root at a, so I'm going to get an a to the n, and it is a causal system, so I'm going to get a u of n type term. So getting the unit impulse response is also quite easy. Remember that a unit impulse response is an external measure of a system's behavior. You take a hammer, right, that delta function, you whack the system and you see what comes out. If there are modes or parts of that system that are not visible to the input, so it's not observable, for example, which is indicative of that pole 0 cancellation that we just saw, having this 0 cancel with this pole, we might get an impulse response that doesn't have as many modes as you would expect for the order of the system. This is a second order system, but we see an impulse response that only seems to have a single mode going on in there. And that's partly because of that cancellation that was going on. Still, we've got a transfer function h of z. We're able to also get the h of n on this as well. What other kind of things did we ask about? Well, we asked about stability. Stability at this point, I think, is also easy to talk about. Stability, right, it requires what? It requires that those poles be inside the unit circle. We need that impulse response function, h of n, right, to be exponentially decaying, not growing. So for stability on this, if I look back at the original, even if it was before I did the cancellations, I had a z plus a and a z minus a. Where are the roots on this guy? We have something at a value a, and we have something at a value minus a. Now, if a were complex, this might get rotated, but we've got a pair of guys. They have the same distance from the origin, right? Norm a. If they're going to be inside the unit circle, I need the size of a, the absolute value of a, to be less than 1. So stability here, to get us so that we can have roots inside the unit circle, requires the size of a be less than 1. If I have norm a less than 1, that would imply that the system is stable, because that would ensure that the roots, even the ones that I can't see because of the 0 covering it, are inside the unit circle. So a condition on that multiplying parameter that we saw in the original structure. I can also think about how I would get the difference equation description of this system as well. I could try to get the difference equation description from the simplified version of h of z. That would not be reflective of the actual internal workings. So I'm going to work with this version of the transfer function that's in the negative powers of z, that will give me a delay form difference equation. And before I did any kind of cancellations in there. So if I simply take this 1 plus az to the minus 1 over 1 minus a squared z to the minus 2, remember that that is equal to output over input, cross multiply again, which actually we had before, right? And then invert z transform this guy, we should be able to get the difference equation. What do I get in this particular case? I'll see if I can get both of these in there. I'm going to have a y of n, and I'm going to have a minus a squared. Z to the minus 2yz would just give me a y of n minus 2 delayed by 2. Get the x terms on it. I'm going to have x of z times 1, inverse transform that. That's just an x of n. And then I had a plus az minus 1 times x of z, invert z transform that. I get a plus a. And then the z to the minus 1 just makes that input delay by 1. So I can see in this particular case that if I take that original transfer function h of z, especially before I did any kind of cancellations, I can get a difference equation description that reflects the internal structure of the system. Even though the system is not one of those ones that is both controllable and observable, it is got a difference equation that I can get from the z transform analysis that we've done. This particular one, as you know, had the pole and zero, one of the poles and zeros lie on top of one another, so you wouldn't be able to externally see those. The last part I think that we were asking on this was, what is the output to a particular input? So we said, what is the output, right? Y of n in response to the input x of n being equal to 1, right? And then we had in there a plus cosine of pi n. I'm going to write this in a slightly different way. I'm going to write this as a 1 to the n plus a minus 1 to the n. If I look at 1, right, 1 is just a bunch of constant values 1. That's like this. So if I look at this value 1, right, it looks like this guy. If I look at this cosine pi n, just start putting in values of n, I would get cosine of 0, that's 1, cosine of pi, that's minus 1, cosine of 2 pi, that's 1, and minus 1, and 1, and minus 1. Well, that's the same as minus 1 to the n. So a completely equivalent, identical form is just 1 to the n and minus 1 to the n. Why did I do that in this case? Just because it made things a little bit easier. We had previously studied this idea that if you have an everlasting exponential z to the n going into a discrete time system, what comes out? Z to the n times this h of z. I've got this result that we derived before that can be applied to this sum condition. Because it's a linear system, I can deal with each term separately. What's the value of z for the DC term? The value of z for the DC term is 1. So how does 1 to the n go through my system? Well, it's going to come out 1 to the n times h of 1. What was h? H was z by, if you go back up to what we had as our h, it was z by z minus a. Let's go ahead and do that. That was going to be a z by z minus a, right? If I do all that, evaluated at z equaling 1. So that's going to give me a 1 to the n, and then I'm going to have a 1 by 1 minus a. So 1 to the n is just 1, and so this whole thing is a 1 by 1 minus a. My DC term of 1 comes out changed, and it's now going to be 1 over 1 minus a. If you had a value of a half for a, for example, you would end up having the 1 come out as a 2. And all of these can be done for different values of a. If I look at the minus 1 to the n term, right, minus 1 to the n is just a different value of z. It's going to come out as minus 1 to the n times h of minus 1. Well, that's going to be minus 1 to the n, and then I'm going to put minus 1 in for z, and that's going to be a minus 1 over minus 1 minus a, which is going to be a minus 1 times 1 over 1 plus a. Now, if that factor 1 plus a was complex, you might get a complex output. If a had a particular value that was positive or negative, you might get a different term. But in the end, we just get a pretty simple expression, minus 1 to the n times this overall factor, a constant, 1 over 1 plus a. If I wanted to return that minus 1 back to its form of cosine pi n, I know that this is completely equivalent to saying this is cosine pi n times 1 over 1 plus a. So I'm just going to quickly summarize. If I have an x of n in this case, which was sort of a special case, but I had a 1 plus cosine pi n on this guy, right? I just used frequency response type concepts on there, and I found out that my output y of n was equal to that 1, right, became a 1 minus 1 over 1 minus a, 1 over 1 minus a, and the cosine pi n became a 1 over 1 plus a times that same cosine pi n, and I'm done. So we've finished the two examples I hope to do. This concludes our study of the chapter 5 stuff, the Z-transform stuff. Coming up next, we are going to start our talk about Fourier, which is a lot of fun as well. So next time we'll start Fourier.